talked about the MAC addresses already, how they're burn-in addresses, a unique identifier on the network card, and they're really easy to spoof. The original design was EUI on MAC48. They're 48-bit hexadecimal addresses. For the first half is the manufacturer ID, and the last half is the device ID. The EUI on MAC64 addresses also use the first 24 bits for the manufacturer, but the last 40 for the unique ID. We have more devices. We need more address space. The only thing we haven't covered so far in how it works is IPv6 only uses 64-bit MAC addresses. We talked about that. The way they do it is they add FFFE into the device identifier if the device on the network that uses IPv6 is only a 48-bit MAC address. That way they make it into a 64-bit MAC address. So let's move into something we haven't talked so much about, IP addresses. They were first deployed for production in the ARPANET in 1983. ARPANET later became the Internet. It was developed in the 1970s for a closed secure network, DARPA, or Defense Advanced Research Projects Agency. See the keyword there? Defense? It's military. And since it was on a closed and secured network, security was not built in. That's why we have all the protocols we do now that add security to it. We bolt it on. But just like any other bolt-on security, it's not as secure as if it was designed in. IPv4 inherently is a connectionless protocol that's used for packet-switched networks. So since it's connectionless just like UDP, that's why we had to build in the TCP protocol. It's based on a best effort delivery model. It doesn't guarantee delivery, doesn't assure proper sequencing, and it doesn't prevent us from delivering the same thing twice. Because of all these flaws, we've added a bunch of protocols to get the reliable traffic that we need for our networks now. IPv4 is still the most commonly used protocol on the internet, but because of the limited address space, we're slowly moving towards IPv6. But the move so far is mostly happening on the back end. You may have heard that we're running out of internet addresses 5-10 years ago, and it's actually technically true. But since many devices are now ready for IPv6, what we've done is we've redesigned the back end to use IPv6. IPv4 only has about 4 billion usable addresses, and there are, I think, 8 billion as of the last count devices on the internet now. So for instance, for cell phones, any cell phone carrier in the US uses IPv6 for any smartphone. You don't know, you don't care. Your phone is IPv6 capable, so they can save all the IPv4 addresses they've used previously for cell phones and use them in areas where they're actually still needed. When IPv4 was designed, 4 billion seemed like an insane amount of addresses. We would never run out. But obviously they failed to predict how popular the internet would be, how many connected devices we would have. See here below a comparison between IPv6 and IPv4. IPv4 has just slightly over 4 billion addresses. I'm not even going to try to pronounce how many IP addresses IPv6 has. But for those of us, like me, who are not math geniuses, someone broke it down to every square foot or every 30 by 30 centimeters on the entire planet Earth could have 65,000 IP addresses. That's how many IPv6 has. So I think, for now, we're okay on IPv6 addresses, regardless of how many devices we decide to put on the network. We talked about the destination IP and port earlier, and this is the example I used from earlier too. The IP address is the building, the port number is the apartment. This is the way that our computers tab if you have 50 browser windows open, 2 games, videos playing, and whatever else you do online. Each of those windows or applications uses a unique port number. We have 65,536 unique ports we can use. Ports 0 to 1023 called the well-known ports. These are where most of our protocols live. Each port is assigned to a specific protocol, and it's only used for that. So port 80 is used for regular web traffic. Port 443 is used for HTTPS or secure web traffic. Port 1024 to 49,151 are most commonly assigned to specific vendor applications. A vendor can apply and get assigned a specific port only to be used for their one application. And then from 49,152 to 65,535 is the private, manic, or ephemeral ports. They can be used by anyone for anything. And the ephemeral ports are the ports used by your web browser. You open up a web session to IST², the application assigns you a random port in that range, and when IST² send the traffic back, they send it to that one port. Let's look at some of the common ports, and for the exam, I would know all these ports, the port number, what they do, and if they're TCP or UDP ports. It's not a terribly long list, but there is some memorization here you need to know. Port 20 and 21 are FTP ports. They use TCP. Port 20 is used for the data transfer, and port 21 is for FTP control. Set up the sessions, make sure the data is delivered, all that stuff. Port 22 is SSH, or Secure Shell. It uses both TCP and UDP protocol. Port 23 is only TCP and is for Telnet, and Telnet really is the predecessor for SSH. It's what we can use to connect to remote systems, but it is unencrypted. Everything is sent in plain text, so it's easy to sniff. We never want to use that. I'm going to bundle some of the ports together here. Port 25 is for SMTP. It's a TCP port. We use it for our email programs. It can also at times use port 2525. Also for emails, we use port 110 for POP3 email. And if we don't use port 3, we might use IMAP, which is port 143. It's also a TCP connection. Most connections are TCP because we want to guarantee the delivery. So 25, 110, 143 are the common email protocols you should know and their port numbers. Port 80 and port 443 are for web traffic. Port 80 is HTTP, Hypertext Transfer Protocol. That's regular unsecure web browsers. They can at times also use port 8008 or 8080. And then 443, like I said, that's secure web browsing. It's again the Hypertext Transfer Protocol, but over TLS or SSL. And in your browser window, you'll see the HTTPS. S is for secure. Port 137 and 138 are for NetBIOS. 137 is for the name service, username registration and resolution, and then the actual data is set on 138. And the actual data can be sent both at TCP and UDP. And then finally we have port 3389, which is Microsoft's terminal server or RDP connection, where you can connect to other servers using, well, RDP, Remote Desktop Protocol. It uses both TCP and UDP. Since it's above port 1024, it must be a vendor protocol. So that port is assigned to Microsoft, whereas you can see all the other ports are below 1024. They're non-vendor specific protocols. When we talk about IP addresses and ports, they can also be called a socket. A socket is one set of an IP and a port. Since UDP is a connectionless protocol, it only uses one socket, an IP, and a port. TCP uses a pair of sockets, or really two individual sockets making up the pair, since it needs that bidirectional communication. You'll have an IP and a port, but both the source and the destination. If you look over here on the right, this is a session from me browsing ISC² website. You can see my source pair. It's 192.168.0.6:49691. If you know a little bit about networking, you can see that my address is the local address. And then the port number is the ephemeral port that's randomly assigned to my session, in this case 49,691. You can see all the way to the left it's a TCP session, so there should be a socket pair. So the third line is the destination address. The ISC² website's IP is 195.122.177.218, and then the port number. In this case, you can see the port number is HTTPS. It's very common to translate well-known ports into what they actually do. Since port 443 is the HTTPS port, it just translates directly into that. And then the last column, you can see my session is established. How IP addresses are allocated is handled by the IANA, Internet Assigned Numbers Authority, which is the department of ICANN, Internet Corporation, for assigned names and numbers. Don't worry, there'll be a lot more abbreviations in this section. IANA has divided the world into regional internet registries, or RIRs, where in those areas, regional organizations delegate the address space they have control over. You can see on the map here on the right, they've divided the world into 5 major areas, and each of those have an organization that handles IP address assignment for that area. Afrinic handles all IP address assignment in Africa. ARIN handles United States, Canada, some parts of the Caribbean, and Antarctica. APNIC handles Asia, Australia, New Zealand, and many of the Pacific countries. LACNIC handles Latin America, Mexico, and parts of the Caribbean. Finally, RIPE NNC handles Europe, Russia, Middle East, and Central Asia. These organizations are by far mostly active on the IP4 network, where each area has a set of assigned IP addresses that they can then distribute between their countries and the internet service providers they have. If you as a customer need a static public IP address, you would contact your internet service provider, they would assign a public IP to you, and then you'd give them some money. They would use one of the addresses from their own pool. At the time when we were running out of IPv4 addresses, a lot of shuffling was done to extend that period of time. And part of what they did was they reassigned the address spaces for each of the regions. I think at the time Africa wasn't using very many of the IP addresses, so IANA claimed some of those and assigned them to some of the other regions. Before we continue on the IP addresses and the port numbers, let's look a little bit at the different types of traffic we can send and what's unique about each. Unicast is one-to-one traffic. This is traffic from me as a client to a host and then the reverse traffic. If, as part of our forensics or our monitoring, we want to capture all the unicast traffic on our network, we can attach a device to our switch, which has its network card in promiscuous mode, meaning receive all traffic, and then the port on the switch we'll configure to be a span port. It could be our network intrusion detection or our network intrusion prevention system, where we look at all the traffic on our network to ensure nothing's malicious. You can also use multicast. This is where one client sends to many, but it sends to a predefined list. Whatever traffic we're sending, we send to everybody in that list. And whereas multicast is one to many, broadcast is one to all. The traffic is sent to everybody on that local segment. If it's a limited layer 3 broadcast, remember layer 3 has IP addresses. We would use the IP address 255, 255, 255, 255 as the broadcast address, but it's important to note here a router will not pass limited layer 3 broadcasts. They will drop the traffic. So whenever the traffic hits a router, it will be dropped. Limited layer 2 broadcast uses MAC addresses because, well, MAC addresses are layer 2 protocols. So if you want to broadcast something on layer 2, you would use FF:, FF:, and so on as a broadcast MAC address. That would then send it to all the nodes on that local segment. It is very common for our networks today, even though they're logically connected and they have that and they're on the same IP range, to be separated by routers. So for that, we can use a directed broadcast. If, for instance, our accounting department is located in 3 separate remote buildings, as long as they're on the same network segment, it doesn't care how we're physically connected. All it cares about is the logical segmentation. If our accounting department has the private address of 192.168.19.12/24, then a directed broadcast will be sent to all the hosts on that network.